Welcome everybody to our Gamma seminar. Today we have the pleasure to guest Joanna Gonera, who is going to talk about the Fermat principle in general relativity via the Herglotz variational formalism. This is a work with Joanna Piwnik and Piotr Kosinski. So Joanna, thank you very much for accepting our invitation. It's a pleasure to have you here. The floor is yours. Please go on.
Hello everyone, and once again, thank you very much for the invitation. I will talk about our quite recent paper from Nuclear Physics B, which was written mainly by my PhD students, and of course it was made with me and the head of our department, Piotr Kosinski. And the title is Fermat's Principle in General Relativity via Herglotz Variational Formalism. So I will first talk about some tools I need to show you how to formulate Fermat's principle. First, I will talk about Herglotz variational principle and Herglotz formalism a bit. Not that much. And then just few words about reduced dynamics for homogeneous Lagrangian. And then I will show you what the problem is with Fermat principle in gravitational field. And at the end, I will show you two examples how it might be used in two metrics, Magritte and Kessner. Well, this is something we all know as principle of least action. We have a curve in configuration space and we define the action functional. And the dynamical evolution in the interval is obtained by demanding the stationarity of action with respect to variations and fixed points, fixed ends. And we know that at the result, we obtain the Euler-Lagrange equations. The same variational principle we can define in different way. We can say that we might just consider the differential equation for the action being the derivatives of Lagrangian with some initial conditions for action and for the variations of Q, and of course the variation of T, it should be T0 probably because it's at the beginning. No, this is the condition, yes, which allows us to show that this formulation is actually equivalent to the one I showed you at the previous slide. So now, if we know that, we can ask, okay, what if Lagrangian depends on the action? Well, let's try to perform variational principle for that Lagrangian at the manner, the second one manner. So we start with the Lagrangian, which depends also on the action variable S here. Of course, Q and Q dot, just coordinates and generalized velocity, it might be in any dimension. Yeah, you can imagine that just for simplicity, it's just put Q, but it might be QI. Now, what are the initial value problem for this? So we have a curve Q, Q on T, and we put the initial condition that as the action at T0 equals S0, And of course, we have this variational of Q at T0 at T1 to be 0. And what we believe is the variational principle is that demanding that under this condition, the variation of action at T1 is equals to 0. All right, so what we do, we just write down everything we know about this relation. There should be plus, not equal, of course. And then we just check. What we notice at the third line is that actually, because as dot is equal to L, we obtain the ordinary differential equation, the linear one, for delta S. And of course, it's easy to solve that. Well, the general form is there, written here, and C dot has to be, there is a condition for C dot. This is just the normal way we are solving the differential equation. All right, so what's the next step? Because delta S 0 is 0, the initial condition doesn't change. And also, the variation of Q at T0 and T1 at the ending points are 0. Well, we can use this, and just like in ordinary mechanics by integrating by parts, we obtain the equation which we see is very similar to the one we obtained usually when we get the Euler-Lagrange equations, but they differ by one part. So we see that actually the variation of S1 is 0, provided the Euler-Lagrange Herglotz equations are satisfied. So this is, you see, just a kind of generalization of usual mechanics students learn at, I guess, second year of study. But this is, of course, special case, actually very different, because we don't have 2n dimensions, but 2n plus 1 because of the S here. All right, and what's more,
Joanna,
yeah.
Sorry, one question. What do you want to do at the very end with this? What systems are you going to study? Because you know there are formulations with these in geometric mechanics with a nice picture with quantum geometry and things like that.
I will show you. This is just to use it to obtain Fermat principle. Because if you want to, if you want to do that for the gravitational field that depend on T, and you want to do that at Lagrangian level, you obtain Lagrangian, which depends on x0, and x0 is actually the action. So now I'm talking about tools. Just
just one question. Let me ask you because I'm curious. Yeah, and how it depends on the action. They're linearly.
Yeah.
It is linear dependence, or which type of dependence on the action we have?
Yeah, I will show you. Like now it's just you see, you don't know how it depends. It doesn't matter actually.
Okay,
of course.
no, that's good. Sounds good. Thank you.
Okay, so now we are going to Netter theorem, the generalized Netter theorem of, or we can say Herglotz Netter theorem. So we are consider general point transformation. And the first thing is how does Lagrangian change after this? And it's not very difficult. It's just, I guess, 2 lines of calculation to show that if we define the new Lagrangian from new variables, as it's written here, then this new Lagrangian gives us the Euler-Lagrange-Herlotz Lagrangians of this form, which are equivalent to the initial one. Okay, so it is how does the new Lagrangian look. You can see that, or maybe I will show the next slide. All right, so now we want to consider symmetry because we are going to Netter theorem. So what is the condition of the symmetry? Is that the functional form of the new Lagrangian should be the same as the original one, the initial one. Okay, so starting from the Lagrangian written here, we just skip the prime at the L on the left-hand side. And this is our condition. You see that there is no total derivative here. Well, that's what we are, what we actually expected, because usually we have, if we consider Netter theorem, the new Lagrangian might differ by total derivative. But actually there is, because if you, well, you can consider just standard mechanics here, because it should works if S doesn't change. Yeah? But if you add the total derivative, action changes. Okay, and if this derivative is just, well, this is total derivative of the function of coordinates and t. And if you write down that S prime is equal S prime plus some function, Lagrangian change about the function of Q and T, then we see that actually what's written here as derivative the S prime over the S is 1, of course, but this two first terms gives just the total derivative of the function. So this is how does the Lagrangian change. So it's included here. Yeah, we don't have to put it in. It's just included. Okay, so we are very close to Netter theorem. So we are considering now the infinitesimal transformations. And as usual, we just write down and just like in the normal mechanics. But as you see, of course, if we use the equation of motions, the second and third line disappeared. But still, we have not only d over dt of something equals to 0, but we have the 1 terms more. So, of course, we can integrate it. And the conservation law differs by the term a to the minus integral of something. And that's not very nice. It's not very nice because we see that to know this integral, we have to know everything. It's not the local factor. We have to know Q at everywhere. So it seems to be not very useful, but what we see next is that this factor is universal. It's for all conserved quantities. So to obtain the integral of motion, which is useful, for which we don't have to solve the equation of motion first, it's enough to take the ratio of this. So if we have n integrals of motion, we can always construct n-1 integrals of motion, which are useful for us because they gave us the relationship between Q and Q dot. And we don't have to solve the equations of motion first, Herglotz, Euler, Lagrange equations. It is also possible to construct Hamiltonian formalism. We just, as usual, as in the usual mechanics, we can define the momenta by the partial derivative of Lagrangian by Q dot, and just perform Lagrange Legendre transformation. But the canonical equations are a bit different than we are used to because we have the partial derivative with respect to action. We can also define something which is called Mayer bracket. It is also possible to define others, probably, as I remember, they are called Jacob bracket, but because in our work it was Mayer, so the Mayer bracket is defined as we can see here. We can write down the equation of motion or time derivative for any function. We see that it is different than in standard mechanics. It differs by this part concerning derivatives with respect to action. And also, as you can see, the properties of Mayer bracket are a bit different than Poisson bracket because, of course, it's antisymmetric. We have the property of linearity. We have also the Leibniz property, but the Jacobi identity is really different. If you want to define, that's probably Jacobi bracket, then you have the standard form of Jacobi identity, but the Leibniz property doesn't look in the normal way.
Joanna, here's a comment, because I think that you are doing this from a physical point of view with physical references.
Yes.
Yes, to translate it a little bit into geometry.
It's
because
contact.
there is there is a bracket that is contact, but it's not of this type. Yeah, it does not satisfy the Leibniz property. And this is the standard one, the standard property. And there are Hamiltonian vector fields in contact geometry that they are the ones you are describing. Then there are others. They are the evolution vector fields. I think that Manuel de Leon, for example, introduced them, or some of his collaborators, something like that. I don't remember exactly. And with that, you can construct a new bracket. And this bracket, it does not, it's antisymmetric, it satisfies the alignment property, but it does not satisfy the Jacobi identity. It's exactly the one you have there. Is this geometrically. And in these works, I haven't seen it, maybe Narciso or someone of the persons know it. But the fun thing is that when you have contact geometry, you have all these brackets, you always have that Lie brackets, morphisms of Lie algebras and things like that. It does not work here. Indeed, this Jacobi bracket is interesting because it seems to be described by means of the other geometric structures, really, truly speaking. And this is quite interesting because they are not, for example, they are not Poisson bracket. Have you done something with this fail of the Jacobi identity? I mean, have you somehow used it or found something interesting?
I just wanted to show you that it is just possible to write down the Hamiltonian formalism, yes. And well, you might actually, I will speak like physicist because I'm a physicist.
Yeah, it's cool. I mean, it's another way of,
Yeah.
But I mean, the fun thing is that we can translate one into the other, and sometimes problems on one field, they are not known in the other on the other one. See that? Please go on. Joanna.
So this is just, I mean, you can also write down the, well, let's say generalization of Hamiltonian Jacobi theorem.
Yeah, in this is some of the things I work with Julia. Okay. It's related.
All right.
And the bracket we use it to show the integration of partial differential equations. But anyhow, please go on, because I will not let you to talk.
It was just the one tool. So we have Herglotz mechanics. We have Herglotz Lagrange Euler equations. And well, we go to do the second tool, and this is about homogeneous Lagrange. So let's imagine we have an n+1 degrees of freedom. n+1 because we have Q0 here, which is quite important. And we have to have some conditions. So first of all is that R is non-degenerate. So it is always possible to solve some equation. We have no constraints. What's more, L does not depend explicitly of the evolution parameter. And the third condition is that L is homogeneous function of generalized velocity of degree 2. Well, okay, I will show example later. Then, of course, this is normal case. I mean, the L does not depend on the action. It's just normal, standard, classical mechanics. We have Euler Lagrange equation, and we see that actually, because there is no explicit depending on the evolution parameter, we see that the energy is conserved. So actually, the energy, when we express this in Q and Q dot, use just Legendre transformation, and we see that for this type of Lagrangian, which is homogeneous function of generalized velocity of degree 2, we obtain that E is equal to L, and the L is the constant of motion. Okay, so this is homogeneous Lagrangian. And now we consider the subject of trajectories corresponding to a given fixed value E. So that's our equation, and we choose some E. And what we do, we can, because the L is not degenerate, we can solve this equation, at least locally, with respect to Q dot 0. Okay? And of course, Q dot 0 is the function of other coordinates, all coordinates, and other velocities. And of course, it depends on the E. Now we put this solution to L equal to E, and we obtained identity. Okay. This is something we can do just very easy. It is something you can see and then believe that it's true. So we see that if we use if we now write down the derivatives of Q dot 0, we actually obtain this equation. And for this one, we also use here maybe we obtain this equation, and now what we do, we just imagine that Q0 is equal to S. Let. Okay. And if it is so, then the new Lagrangian, the Herglotz one, is just Q dot, Q0 dot. Okay. All right. So we write down the Herglotz Euler Lagrange equations for the Herglotz Lagrangian. And we use the identity we just derived out on the previous slide. And what we see is that if original Lagrangian obey the Euler Lagrange equation, then this is equal to 0. So we have these two things. So for this homogeneous Lagrangian, we can use the Herglotz variational principle, Herglotz or Herglotz formalism. And of course, we can show that this is equivalent. I mean, if you start from the original, if you start from Herglotz or Lagrangian and this and put some condition, you can obtain all, well, at least locally, and if everything is all right, of course, if it is possible, smooth and or conditional holds, then you can obtain from these equations here the standard Euler Lagrange equation for the Hamiltonian, the initial one without action. Okay, so this is a special case if you have this homogeneous Lagrangian. You just can calculate one of Q dot, which is Q0 dot, And then you can write down the Euler-Lagrange equations for this Lagrangian using the identity that L is equal E. If you put the solution of Q from the equation L equals E to this equation, right? So we see that there is equivalence. So if we have something like that, it is possible to write down the Herglotz formalism, and we just reduce space to less dimension. Right? Okay, so we have all tools. And now we talk about Fermat principle. So this is something we learn at school, that we know the light ray moves between points A and B along a path that minimizes its travel time. This is, I think this is at secondary school something. It's not very difficult to write this Fermat principle for flat space star. It has the form right here. Key I is just covariant components of a wave vector, and integral runs along a light ray trajectory. Okay, it's what's important here is that we have to put the condition that the frequency of light is constant. Okay, so now how to turn on gravity? Okay, so well, we know that the general relativity is connected with space-time geometry by the definition of Lex element. And some just names that we see that the constant gravitational field is when we can choose such coordinates that all a derivation of x0 are equal to 0. Does not depend on x0. And if additionally g0 g0I of x is equal to 0, then we say that this field is static. Okay, so we have something which is called equivalent principle. So we think that we can from this conclude that actually it is possible to write the Fermat principle also for constant gravitational field. And that's not very difficult to show. I guess a very nice way to show it is at Landau book. And what we obtain is here that the Fermat principle is just the variation principle for the expression written here. And that works, of course, for all constant gravitational field. I mean that also for static and for stationary. There are some symbols here. The L is just the space metric. It's only on, we do not consider x0 here. And it's given by this equation. And Well, that's okay, but you can look at this a different way. So you see that if we solve the s squared equals to 0 with respect to the x0, we obtain exactly what we have here at this variational condition. Right? So actually, the Fermat principle for constant gravitational field, we might write as written right here at the end of the slide, and it looks very nice. It looks very nice. Okay, and this is known for a long time ago. All right. You see, we can now define the x0 over the sigma as the new Lagrangian, and then this principle just becomes the normal standard variational principle of Lagrangian mechanics. Okay, if we define our Lagrangian at this way, we obtain just variational principle of standard Lagrangian mechanics. And notice that nothing depends here of x0 because this is constant gravitational field. So we have standard mechanics. We can write down the Euler-Lagrange equations. And from that, we obtain just the shape of curve that light travel. Yeah. So some remarks here. What we see is that L is a homogeneous function of first order. And we can choose sigma as an arbitrary parameter of trajectory. And we can choose if L equals to 0, we can choose this parameter as a other coordinate. And then we have just the problem from the two-dimensional dynamics. And the second one is that, as I showed you, we actually have two solutions to the equation the squared equal to 0 with plus here and minus. We choose the one with plus, but of course we can choose the other one, and it just means that we can parameterize this curve clockwise or anti-clockwise, so we can move forward in time or backward. Okay, but this was for constant gravitational. On the other hand, what we know is that we have this condition that light moves in such a way that the forward vector, the wave forward vector, is constant along trajectory. Okay, so we can, of course, covariantly. So we can write down the condition, which is written here, and this is just the equation, geodesic equation for light. And sigma is, of course, as usually, the definite parameter, just say it's chosen in the way that everything works. And this one we can obtain from the variational principle written for the Lagrangian written here. This is just d squared, 1/2 of d squared. And but we also need the condition that d squared is equal to 0 because this is light. Okay. Of course, this geodesic equation should give the same trajectory as Fermat's principle. And we see that here we do not need that gravitational field is constant. So what we would expect is that we can write down Fermat's principle for arbitrary gravitational field in a very similar way to this one, where to the constant gravitational field. Okay. And that's okay. So here we have this Lagrangian just ds squared. And what we see here is just we try to look at this Lagrangian on this condition with this Lagrangian using the tools we know. So first of all, this Lagrangian is homogeneous of degree 2 in generalized velocity. So as I showed you before, we can define the Herglotz Lagrangian defined as the x0 over the sigma, just like it actually looks like in the previous case, but what we see here now, well, it looks the same. But now G depends on x0. So our Lagrangian is really the Herglotz one. And this condition, the x0 over the sigma equals Lagrangian, is the first equation of Herglotz Euler-Lagrange. And the second is just the counterpart of Euler-Lagrange equations. Just like I showed you when I talked about Herglotz formalism. So we can, using these tools, we can write down a very nice Fermat principle as the variation of the x0, just like for constant gravitational field. And that's actually the main point here. Okay, so if we use these tools, we can write down the Fermat principle for arbitrary gravitational field. Okay, I will show you some examples. So first we talk about Schwarzschild-de Sitter metric. Well, it seems first not to be very interesting because it's at least between two horizons, it's constant gravitational field. But we can make some changes of variables to something which is called Mag-Witt metric. It's written here. And then, as you can see, the tensor metric depends on t. Well, x0 is t here, okay? And we can write it down by black hole as cosmological constant and Hubble constant, which makes it more physical. Now you can see that if we put lambda equal to 0, the cosmological constant, and define rho as the function of R, this matrix reduces to the Schwarzschild one. Okay? What we know about this? We know that it's spherically symmetric. It's and that's important because we know also that the constant of motions. All right. For this one, we can write the new Herglotz Lagrangian. As you could see here, we choose the affine parameter to be the angle fit. And Lagrangian looks at this way, not very difficult. And the equation of motion are right down here. Dot is every dot. It's just derivation with respect to phi. Right? Now, we are looking for integrals of motion to solve the equations, to find the easiest ways to solve the equation. We consider, this is actually because we know a lot about Schwarzschild, the Sitter metric, it's quite easy to write down the symmetry transformation. Okay? And we obtain two constant of motion with this horrible factor here, to the minus something. But as I said before, we can construct the integral of motion, which is useful, which does not demand to solve first the equations of motions. So we take just the ratio of C1 and C2, and we obtain the integral of motion. So our two equations reduces to, well, also two, but it's very easy to solve them, and we can obtain the relation between t and phi. Or okay. Yeah, but you can say, all right, but this is still static field. So let's talk about really, depending on the time, gravitational field. And this is Kastner metric. And this metric described an anisotropic universe, the vacuum one, there is no matter. And it expands and constructs in different direction, differently, let's say. Yeah? And the Kastner matrix written here, and P1, P2, and P3 we have this Kastner condition on this P1. This is just the numbers. We can write down the metric tensor here and Christoffel symbols, and we see they are all is explicitly depending on t. It's not very difficult to write down the geodesic equation for this matrix. And of course, we have this big Lagrangian here, L, and we can write down the constant of motions. we had the constant of motion here are generalized momenta and Lagrangian itself, which is equal to 0. Now we can write down the Herglotz Lagrange equation function, which is here. And we are choosing now the affine parameter to be x3, and the Lagrangian looks like here. We can construct the integrals of motions. We have 3 of them, and of course we know that we can construct only 2 which are independent, which are in the form which is useful, yes, because this J here is this universal factor. And at the end, we have actually 3 equations for T and x dot 1, and from this we can find T x dot 1, probably that should be x dot 2. So we can solve this, and they are just equivalent to the geodesic one. So we can construct the other Lagrangian, we say reduced space, yeah? Yeah. Okay, some conclusion at the end that maybe this is again very physical one, but there are other formulation of Fermat principle for arbitrary gravitational field, and one is spoken like this, that we have point P. We emit light from point P. These are null geodesics. And we consider the set which ends at the wet line of our observer, point Q. And the light ray is characterized by the property that its arrival on the lambda of this wet line of our observer is stationary with respect to first order variation of the null curves of this time. But it's not very difficult to show that this is equivalent to what we obtained. We reduced to the space where there's no x0. And if we consider the reduced curves belonging to the infinitesimal neighborhood of the reduced trajectory of light ray, we can lift that to the big space with x0. And since the S is stationary and is just x0, we know that also our ending point is at the word line of the observer lambda. So this is, it's possible just to show that this is equivalent. There's also possibility to extend this to the for the particle with mass, which is not equal to 0, not only for lights, for some particles, but we have to remember that here we cannot choose the affine parameter to be the other coordinate. because as there is now this symmetry for reparametrization of parameter sigma. Yes, if you change parameter sigma, we change ds here because there is no zero, but on the other constant. And actually, that's everything. It's 1 hour, so it's a long time. This is all I wanted to say today. So thank you very much for your attention. And that's it. Thank you.
Thank you, Joanna. It's been a very nice talk with very nice, good examples. So, is there any question, comment, remark?
Yes, please. Can you hear
No,
me?
Narciso.
Okay.
Yeah, we hear you.
Yes. It's just a question. It's about the definition of constant or static metrics.
Yeah.
I think it's in the slide 19.
Yeah.
Can you show?
Okay.
Yes, in fact.
Yes.
Okay. Then the definition of, let me read. The field is called static when G0 I is equal to 0.
0, yes.
But if you take orthogonal or orthonormal frames, this always hold.
Yeah. But this is addition. I'm not. Well, okay, but you might. I understand what you want to say. That all stationary field we can transform to the static one. Yeah, this is yeah, okay. But you see this. Well, sometimes it is just. This is just. Convenient to. Well, I guess that's possibly true, I might say. But I think that we just might consider the metric, which is at this form, yes? When we don't, well, let's say it rotate, it's not maybe very nice, the best word. Huh?
It seems that this definition of a static, it seems it depends on the frame.
Yeah. For static, it doesn't depend. Well, we said that this is constant, yes.
Okay.
But then, I mean, if you write down this classical Fermat principle, you actually choose these coordinates, yes, when they are not, they don't depend on x0.
Okay, thanks.
And this is actually quite important because then the light has the frequency is constant.
Okay, thanks.
Thank you. Is there any other question? Joanna,
Yeah.
do you have any more, or do you know any more homogeneous cases, homogeneous Lagrangians, apart from these ones that you are in here?
Well, probably yes, but I didn't consider them because you can think about very simple one. Yeah? But I mean, this one is spectacular because this is this is the s squared. Yeah, so this is But if you think about mechanics, well, there are some, but I don't think they are that interesting. I mean, there is not so many physics there, but of course,
Okay,
I just
because
didn't think about it. Yeah.
truly speaking, I thought about things like that, but the thing is that I didn't know any example, any good thing. So, and it happens when one is studying mathematical theories that mathematical cases where everything fits, it looks nice, and so on. It's difficult to find something interesting
Yeah,
physical, yeah.
yeah, yeah,
So,
yeah.
okay,
Yeah,
it's been.
that's actually something which is quite new for me, because I usually work on the system which has almost no physical meaning. The meaning is only in my head, yeah. And this is something which has physical meaning, and that's why I like it. Just
Yeah, sure. I have another question because about it was the Kersen metric, yeah? It was called like
yeah,
that.
Kastner, yeah.
Where this comes from? I mean, it's and it's a
Huh.
nice. It's quite interesting, but I never heard of. So how it comes that
Yeah.
someone finishes studying such a thing with
Well,
contractions and dilatation?
actually, there is no discussion metric in our paper,
Uh-huh.
because that's quite funny story. Actually, the uh, well, the PhD thesis, the
Mm-hmm.
doctoral thesis of my PhD student was sent to
Mm-hmm.
the person who is really good in general relativity, and he asked the question about this metrics, and
Yeah.
I'm general relativity is not what I'm really good in. I mean,
Mm-hmm.
so I don't feel as a specialist, you know. So we actually didn't know this metric, of course, so we have to
No,
find it.
may I
But
neither.
this is, I guess this is something, the special case of Bianchi metric, I guess.
Uh-huh.
So
Oh,
it is used to describe the early universe, probably. This is,
oh. Well, it's interesting to see that such a case may have
yeah,
relevant
yeah,
applications. Yeah, I mean that is
yes, yes.
okay.
That's something new for me
Okay,
also.
great. Thank you for all examples because they are for me a source of inspiration where one can apply things and check how it works.
Yeah.
So nice. Is there any other question? No, no. So thanks. Let us thank the speaker again. Thank you, Anna. It's been very nice.
Thank you
And
very much.
okay, so Xavi, you can finish the recording.